This is an exam question which involves using general polar form. It's 2012 paper 1 question 3. So before we start the question we have to explain what general polar form is. So a recap here of the different forms of writing a complex number. The first form we can write it in is Cartesian form, also known as rectangular. And you can see it here on the screen. It's written as a plus ib. On the diagram here it means that it's a units across and b units up. We can also write that same number in polar form in terms of the angle theta and the radius or the modulus r. And it's written as r into cos theta plus I sin theta. And finally we come to general polar form. Now general polar form is based on a simple fact from trigonometry, which I'll explain down here. We can observe from the diagram that I've drawn here that if you have an angle theta, which I've shown in red here, just say for example theta is 30 for example, well that's the exact same angle as if you start on the real axis and go around with the green here back to where we started. So if you go around once, which is 360 degrees, plus 30, which is 390. So what we're saying here in this diagram in effect is that the angle 30 is the same as the angle 390 for example. In general, any angle theta is the same as the angle theta plus 2 pi. And while we're at it, why just go around once? Why not go around 2 times or 3 times? And that's what I've done in the list here. So theta is equal to theta plus 2 pi, or theta plus 2 times 2 pi if you go around the circle twice. Or if you go around 3 times, it's theta plus 3 times 2 pi. In general, it's theta plus n times 2 pi, where n stands for the number of times you go around the circle. So the summary of all that is you can take any angle theta, and it's not really the full story. The angle theta is really the same thing as theta plus 2n pi, and where n is the number of times that you go around the circle. And that's all general polar form is really. It's when you come back to this, all we're doing, if you start with polar form, which is here, you're replacing theta with 2n pi plus theta, which takes into account all the possibilities depending on how many times you go around the circle, 0 times, once, twice, or 3 times, etc. So this here is general polar form. Now, when do you use general polar form? And there's a very simple test you can use in an exam question and so on to know whether to use it or not. And the test is you use polar form when the power is a whole number. For example, if you had something like z equals something to the power of 5, well that 5 is a whole number, so you would just use polar form. But on the other hand, if you had z equals something to the power of a quarter, for example, you'd have to use general polar form. And in the exam question I've picked, we're going to see that the power will be a fraction. It would end up as a fraction, so that means we have to use general polar form. So part A, the complex number z has a modulus 5 and 1/16, so that's r, and an argument 4 pi over 9, so that's theta. And he wants us to write it in polar form. Well, straight away, I mean, the very definition of polar form is r times cos theta plus I sin theta. So that's, in our case, that means z is equal to 5 and 1/16 into the cos of 4 pi over 9 plus I times sine 4 pi over 9. And that's it done already. I mean, find in polar form, that's the first part done. We have found z itself. Now, we also have to find something else which he calls the 4 complex fourth roots of z. So that's something different, and he's explained what he means here. He gives us a hint that w to the power of 4 is z. So we'll write that down. W to the power of 4 equals a z. But he's looking for w. I mean, find the 4 values of w. Turns out w has 4 values. So to find w, if you're being pedantic about it, I suppose this 4 is in the way. So we have to get that 4 out of the way. So, and the way you do that is by putting both sides to the power of a quarter. And that means if you use your rules of indices, the 4 and the quarter cancel. and you have w is equal to z to the power of a quarter, which is all of that there to the power of a quarter. So it's 5 and 1/16, 5 and 1/16 into the cos of 4 pi over 9 plus I sine 4 pi over 9. But of course, as I just said, all of that is to the power of a quarter. Now we can write w equals, it's 5 and 1/16 to the power of a quarter multiplied by the cos of 4 pi over 9 plus I sine 4 pi over 9 to the power of a quarter. 16 by 5 is 80, and 1 is 81 over 16 to the power, if you just tidy that up, it's to the power of a quarter, into, now this is where we bring in general polar form, and the reason is that the power is a fraction. As we saw earlier, when the power is a fraction, you have to use general polar form. So we have to rewrite that as the cos of, I just do a different colour here for clarity, it's the cos of 2n pi plus 4 pi over 9 plus I sine the same thing, 2n pi plus 4 pi over 9, where n is the number of times you go around the circle, 0, 1, 2, 3, etc. And there's another nice simplification we can do here because of the numbers they gave us. 81 over 16 to the power of a quarter. Well, 81 to the power of a quarter is the fourth root of 81, which is 3 by 3 is 9 by 3. Yeah, so that works out perfectly. It's 3. And over 16 to the power of a quarter, well, that's the fourth root of 16, which is 2. So that works out nicely. And I've forgotten, of course, the power is still here. That's still to the power of a quarter. And now the next step is cos. The quarter can now come down in front because of the Moivre's theorem. So it's the cos of a quarter times the angle. 2n pi plus 4 pi over 9 plus I sine a quarter times 2n pi plus 4 pi over 9. Just be very careful with brackets in this question because it gets a bit messy at this stage. But the main thing is that the power is gone. It's now in front of the angle. So that quarter has come down here. That's from using the Moivre's theorem. I might just mention it there, the reason why we can do this, that's the Moivre's theorem. And of course n is from 0, 1, 2 upwards. So the whole point of the question is to find w. It turns out that there's 4 answers for w. We were told the question that there's 4 answers, and this is how we get the 4 answers. W is now this quantity here, and you put in different values of n to get the different answers of w, starting off with n equals 0. So the first 4 values of n, 0, 1, 2, 3, will give you the 4 answers. If you happen to go higher, up to 4 and 5, you'll find out that the answers keep repeating. So that's why we only need the first 4. So putting in 0 first, n equals 0. Well, what happens? W reduces to 3 over 2 times the cos of a quarter. Now the n is gone, so that means that this term is gone. So you're just left with 4 pi over 9 plus I sine a quarter times 4 pi over 9. So we'll keep using brackets carefully. Now the 4 cancels, and you're left with the cos, so you're left with the answer, which is W equals 3 over 2 times the cos of pi over 9 plus I sine pi over 9. And at this stage you could just work that out in your calculator, work out the rest of it. Now n equals 1 is the next answer. So back to the original quantity W up here. We'll put a box around it to distinguish it from everything else around it. So we can come back to the main expression for W, the main equation, and fill in n equals 1 this time. So this n becomes 1. And see what happens. You get W is equal to cos of a quarter times 2 by 1 by pi, which is 2 pi, plus 4 pi over 9, plus I sine 2 by 1, which is 2 pi, plus 4 pi over 9. And to add up that, or to simplify further, you can maybe put that over 1, get a common denominator, and rewrite it as W equals the cos of a quarter times, that's all over 9. 9 2s is 18, and 4 is 22. Plus I sine, the common denominator is 9 and 1, between 9 and 1 is 9. So again, it's the same, it's 22 pi over 9. And of course, actually, I've just realized the 3 over 2 has to go in here as well. That's still there. There's a 3 over 2 in front. So that's your second answer. I mean, you can again tidy up a bit further with the calculator, but yeah, the 4 goes into 22, and just work out the rest of that on the calculator. And you do the same for the last two answers, n equals 2 and n equals 3. So n equals 2, so if you finish it off just by filling in n equals 2 and n equals 3, and that will give you the other two answers in the exact same way as we got the answers for n equals 0 and n equals 1.